Okay, now let's go to the Brynne Packaging case, which is at the end of the chapter in our book. And I have the data right here in my computer. So we'll demonstrate how we could fit the simple regression line using the data analysis pack and using the Brynne Packaging example. So let me share the screen. Okay, and right here, and I think you're seeing this right now, you have the Brynne Packaging, okay, data, and the explanations are given in your text as well. So there's a certain rating given to the employees of the company by the human resources. So it's called WPCT. And the higher this is, supposedly the better performance is expected from the employee. And then we also have the ratings given by the supervisors to these employees. So what we'll do here is we'll use this as our X, WPCT will be our X, and we'll try to predict the rating of the employee using these WPCT scores, okay? So for this reason, I'll go to data, and my data analysis Toolpak is already installed, and I want to use regression here, regression analysis. There is no distinction between simple or multiple. For multiple, you just have to choose the columns. I will input Y range. I will use this. Input X range. I will use the rating. Sorry, I just made a mistake. Okay. Input Y will be this. And input X will be the WPCT. Okay. So input Y, B1 to B26. Now we have labels. Sorry about that. 10 minutes to go, and the warning. And you have some number of things here, but I'm not going to click them. If you click the constant is 0, the regression line will be forced to pass through the origin, 0 and 0. So there will not be an intercept in your equation. Okay, and I won't choose that. Okay, so when I say okay, now I'm going to have actually an output. Now this is very much like the output we saw in our slides. So I'll just make everything here slightly larger. So what do we get from here? Again, multiple R. This is an upward sloping line. So this is the correlation between WPCT and rating, 0.88. R square is the variance in rating explained by the variance in WPCT. Okay, and the standard error on the average, the error made by this prediction is approximately 1 rating point. So since the rating is over 10, corresponds to roughly a 10% error made by this equation. Look at the degrees of freedom here, 23 degrees, n minus, remember, k minus 1. Sum of squares regression, sum of squares residual, and total sum of squares. So when I get to my R square, and actually I compute sum of square regression divided by sum of square total, you can immediately see that's my R square. Sometimes we represent this as a percentage when we do that, and it becomes 78.77%. So we can express this as a percentage of variation in Y explained by X. So now let's go to the mean squares again. Of course, 84 divided by 1, 22 divided by 23. Those are the mean squares. You might also notice that standard error is very close to this. Okay, and the reason is basically the sum of square error divided by n minus k minus 1. And if you take the square root of that, that is the standard error. Okay, that's why they're close in this case. So what's my equation? 0.97 plus 0.22 times WPCT. So if I want to make a new prediction, okay, for a given X prediction, Let's say if X is actually, the rating is equal to 15, what would be my prediction? And I could just say intercept plus the unknown X and my slope, and that gives me 4.29, the rating of 4.29. I don't know if I had already a 15 here. Let me check. I don't think I did. So, but I have, for example, a 13 with a prediction of 4, and I have actually a 16 with a prediction of 6. So a prediction of 4.29 for WPCT of 15 maybe is reasonable. So I could do a prediction using these coefficients. Okay, I could do predictions. I could also do predicted. So I could do all the predictions here as well. So intercept plus WPCT times the slope times WPCT. Okay, and that would be the prediction, the predicted value, and the actual observed value. And the difference between these would be the error. So if I actually calculate y, actual y minus y hat, that would be my error. Okay, and you could do this again for all the values that come below the rating of 3. So now, what is the significance of this model? So let's look at the standard error of the slope, 0.02. Now, this is calculated. 0.22 divided by that. So let me just do this. You see, this is the t-stat. Then I have to check a t-distribution with 23 degrees of freedom. Okay, and when I do that, I will find it, of course, corresponding to an alpha level. And if this t-stat is greater, then I reject the null hypothesis that slope is equal to 0. And here also I have a confidence interval for the slope. So what this is saying is that the slope could be anywhere between 0.17 and 0.27. And 0 is not in this interval. So 0 is not in this interval. So that's why I would not reject the null hypothesis that slope is equal to 0. Okay, now I think this is what I want to say for this topic.